Hello, in this video I'll be working through Unit 2 homework problems 11 through 14. For number 11, suppose that y equals f of x is a differentiable function for which the following information is known. We know f of 2 equals negative 3, f prime of 2 equals 1.5, and f double prime of 2 equals negative 0.25. Is f increasing or decreasing at x equals 2? F prime of 2 equals 1.5, and that's a positive number. So f prime of 2 is greater than 0. And whenever f prime is greater than 0, we know the function is increasing at that point. So f prime of 2 is greater than 0, therefore f is increasing at x equals 2. The second part of that question is f concave up or concave down at x equals 2? Well, our second derivative, f double prime of 2, is negative 0.25. That's a negative number, so less than 0. And whenever the second derivative is negative, we know that our function is concave down at that point. So f double prime of 2 is less than 0. Therefore, f is concave down at x equals 2. Part B, do you expect f of 2.1 to be greater than negative 3, equal to negative 3, or less than negative 3? Well, f of 2 is equal to negative 3, and the function is increasing at that point. So f of 2.1 should be a little larger than negative 3. If our function is increasing, then our y value should be getting larger. So we would expect f of 2.1 to be greater than negative 3, since f is increasing at x equals 2. Part C, do you expect f prime of 2.1 to be greater than 1.5, equal to 1.5, or less than 1.5? F prime of 2 is equal to 1.5, and the derivative of this at x equals 2 would be f double prime of 2, and that has a negative value. So when the derivative of something is negative, it means the function that we took the derivative of is decreasing. So f prime of 2 is 1.5, and f prime is decreasing at that point. So if we go a little bit past that point, like 2.1, we would expect that value to be lower. So f prime of 2.1 would be less than 1.5, since f prime is decreasing at x equals 2. And again, we know that f prime is decreasing because its derivative, f double prime, is negative. Part D, sketch a graph of y equals f of x near 2, f of 2, and include a graph of the tangent line. We know that f of 2 is equal to negative 3, so we can plot that point. So 2, negative 3. We have a point there. And the slope at that point is 1.5, or 3 over 2. So f prime of 2 equals 1.5, or 3 over 2. So to draw the tangent line passing through that point, I need a line that has a slope of 3 over 2. So up 3 over 2. Tangent line is going to look like so. So now we draw our curve so that it looks to be tangent at that point. So maybe something like that. Number 12, for a certain function y equals g of x, its derivative is given by the function pictured below. What is the approximate slope of the tangent line to y equals g of x at the point 2, g of 2? The slope of the tangent line would just be g prime of 2. To find g prime of 2, since we have the graph of g prime, we just go to the place where x equals 2, follow that up, and it looks like it's about right there, so maybe 1.5. Part B, how many real number solutions can there be to the equation g of x equals 0? Justify your conclusion fully and carefully by explaining what you know about how the graph of g must behave based on the graph of g prime. Well, if we look at the graph of g prime, it's positive everywhere because it's above the x-axis. And g prime is our derivative graph. So if the derivative is always positive, that means our function g is always increasing. And if g is strictly increasing, it can only cross the x-axis one time. So there could be at most one x-intercept or one solution to that equation. So at most, one solution to g of x equals 0, since g is strictly increasing. And again, we know that because g prime is greater than 0. Part C, on the interval from -3 to +3, how many times does the concavity of g change? Remember, we're not looking at the graph of g, we're looking at the graph of g prime, the derivative. And to determine concavity, we want to think actually about the second derivative, so the derivative of g prime, or the derivative of this graph that we're looking at. Between -3 and this point right here, which looks like it's maybe -2.5-ish. So here, g prime is increasing. And if g prime is increasing, then its derivative is positive. So g double prime is positive. So I'm going to just color in pink here all of the places where g prime is increasing. And if g prime is increasing, those are places where the second derivative is positive. And then between -3 and 3, g prime is decreasing here, and then along here, 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 and here. And we're not going to go past 3. So it changed concavity whenever I have a color change here, or in other words, whenever the first derivative, g changes concavity wherever the first derivative changes from increasing to decreasing or from decreasing to increasing. So that happens one time right here, one time right here, once here, once here, once here, once here, once here, once here, and once here, for a total of 9 times. Since g prime changes from increasing to decreasing, or from decreasing to increasing. Nine times. Part D, use the provided graph to estimate the value of g double prime of 2. Well, g double prime of 2 is the slope of g prime of x at x equals 2. So when x is 2, we're at this point right here on our graph, and we want to estimate the slope of g prime at this point. So if I draw a tangent line, it's about like that, and then we'll just estimate the slope. So let's go from here, we're going up about 1, 2, 3, and over not even quite 1. So approximately up 3, that's our rise, and then our run, I'm going to call that about 0.8. Which is going to give me 3.75. So g prime of 2 is approximately, now I just estimated that based on the graph and how I drew my tangent line, yours might come out to be a little bit different, but about 3.75. Number 13, a bungee jumper's height h in feet at time t in seconds is given in part by the data in the following table. Use the data to estimate h prime of 4.5, h prime of 5, and h prime of 5.5. At which of these times is the bungee jumper rising most rapidly? So to find h prime of 4.5, we can't find it exactly, but we can estimate it by taking the two closest surrounding points and finding the slope between those 2 points. So that's called a central difference. And basically what we're doing is we're moving a little bit away from the point in each direction and finding the slope of the secant line that passes through two surrounding points. As long as our two surrounding points are reasonably close to the point that we're really interested in, our estimate will be fairly accurate. So to estimate h prime of 4.5, we're going to pick the closest two surrounding points. So it's going to be 69.8 minus 55.5 over 5.0 minus 4.0. And this should be approximately equal to, because that's not necessarily exactly what h prime of 4.5 equals to. That's our estimate of h prime of 4.5. And that is 14.3. And then the units on that would be the change in h, which is feet, per, and then the change in time, which is seconds, so feet per second. H prime of 5. For h prime of 5, we're going to use the closest surrounding points to 5. So we'll do those in yellow. So we want to go a little bit less than 5, that's that point, and then a little bit more than 5, we got to jump down to this other point here. So it's going to be 81.6 minus 60.4 over 5.5 minus 4.5, or 21.2 feet per second. For h prime of 5.5, again, we're going to take the two closest surrounding points. So the point before 5.5 is 5.0, so we'll use that one. And then the point after the 5.5 is this 6.0. We'll use that one. So our calculation is going to be 93.7 minus 69.8 over 6 minus 5. Which is 23.9 feet per second. At which of these times is the bungee jumper rising most rapidly? So that would be the one with the highest slope value. The 23.9 is our fastest rate. So that would be this one, 5.5, at time t equals 5.5. Part B, use the given data and your work from Part A to estimate h double prime of 5. H double prime of 5, so h prime of 5.5 minus h prime of 4.5 over 5.5 minus 4.5. So the h prime of 5.5, we estimated that in Part A, 23.9. Minus the h prime of 4.5, we estimated as 14.3, and then over 5.5 minus 4.5 is 1, so now that's giving us 9.6, and in the numerator, our h prime units were feet per second, and in the denominator we have seconds, so this is feet per second, or we can say feet per second squared. What physical property of the bungee jumper does h double prime of 5 measure? That's going to be the acceleration. So just the h prime of 5 is going to measure the velocity of the bungee jumper. And then if we take the derivative again, we're measuring how quickly the velocity is changing, so that's going to give us acceleration. And the units there are feet per second squared. Part D, based on the data, on what approximate time intervals is the function y equals h of t concave down? What is happening to the velocity of the bungee jumper on these time intervals? Well, if we make a scatter plot using the points that we have, and this is a calculator active question, and then our graph looks something like this. And so it's concave down until we get to this point here, which is 2. And then it's concave up, concave up, concave up until about this point right here. And that happens at 6. So if this is h of t is concave down on the interval 0 to 2, union 6 to 10. And if it's concave down, that means the second derivative is negative. If the second derivative is negative, that tells us the first derivative is decreasing, and the first derivative represents the velocity. So the velocity is decreasing on these intervals. Number 14, we're going to sketch a possible graph for a function on the interval from -3 to 3 that satisfies the stated properties. So for part A, we want our function f to be increasing from -3 to 3, concave up from -3 to 0, and concave down from 0 to 3. So increasing all the way from -3 to +3, but concave up from -3 to 0. So maybe something like this is concave up, and then right at 0 it switches and starts becoming concave down from 0 to 3. So this point right here is where our concavity is changing at 0, and that is called an inflection point. Part B, now we want our function to be increasing from -3 to 3, concave down from -3 to 0, and concave up from 0 to 3. So still increasing from -3 to 3, but we want to be concave down from -3 to 0, concave down, and then right at 0 it switches and starts to be concave up. So right here is where that concavity is changing. Our curve goes from opening downward to opening upward. So that is my inflection point. Part C, now we want our graph to be decreasing from -3 to 3. So decreasing this time, concave up from -3 to 1, neither concave up nor concave down between -1 and 1, so that indicates it's going to be linear, and then concave down from 1 to 3. So decreasing the whole time, concave up until we reach -1. So concave up and decreasing until I reach -1. Then when I reach -1, I'm neither concave up nor concave down. So I'm linear, but I still want to be decreasing. So I'm not going to go up. I'm not going to go straight across. I'm still going to go down until I hit +1. Okay, so for between these 2 points, that's linear. And then still decreasing, but concave down from 1 to 3. So concave down until I hit 3. And part D, this time we want our graph to be decreasing and concave down from -3 to 0. So decreasing and concave down from -3 to 0. So maybe doing that. And then at 0, we're going to switch, and it's going to be increasing and still concave down until we get to 3. So increasing but still concave down.